Tonight, as you settle in and let the room become quiet around you, we are going to imagine, very gently, what a black hole looks like in space. Not as something frightening, and not as something loud or sudden, but as a distant object, very far away, resting in the deep darkness between the stars. A black hole itself does not shine. It does not have a surface like a planet. It does not glow like a star. If you were looking at a black hole floating alone in empty space, with no gas, no dust, and no nearby stars behind it, you might not see anything at all, and that is one of the calmest and strangest things about it. A black hole is not visible in the ordinary way. It is an object, or more precisely, a region of space, where gravity has become so strong that light cannot escape once it passes a certain boundary. That boundary is called the event horizon. The event horizon is not a solid wall. It is not a shell or a surface that you could touch. It is a boundary in space, a point of no return, where the direction outward becomes impossible for light and for anything else. From far away, though, if the black hole is surrounded by glowing matter, that boundary can appear like a very dark circle, placed in the center of a soft ring of light. So when we ask what a black hole looks like in space, we are really asking, what does the space around a black hole look like when light passes near it and when matter gathers around it? And slowly, piece by piece, the picture becomes easier to imagine. Imagine deep space, almost still, almost silent. The background is black, but not perfectly empty. There are faint stars, some near, most very far away. They are small, gentle points of white, blue-white, yellow, and pale orange. Some are brighter than others. Some seem almost invisible, like tiny grains of light scattered across the distance. In the middle of this quiet star field, there is a region where the stars look unusual. Their light is bent. Their position seems softly distorted. The stars behind this region may appear stretched, duplicated, or curved into thin arcs. This is because the gravity of the black hole bends the path of light. Light usually travels in straight lines through empty space, but gravity curves space itself. And when space curves, light follows that curve. Around a black hole, the curvature is very strong, so the light from stars behind it is deflected around it. From a great distance, the black hole may look like a transparent, invisible lens, warping the background sky. This effect is called gravitational lensing. You may imagine it as a calm, circular distortion, like looking at stars through a round droplet of clear glass, except the glass is made of gravity, and the droplet is made of curved space. There is no sound there. There is no wind. There is only the steady bending of starlight, as the background of the universe is quietly rearranged by gravity. If the black hole is not feeding on anything, if there is no nearby gas falling toward it, this lensing may be the only sign of its presence. A dark place where the stars do not look quite right. A silent circle, not glowing, not reflecting, but shaping the light around it. Now imagine another kind of black hole, one that is surrounded by material. Perhaps it is part of a binary star system, where a companion star slowly loses gas. Or perhaps it sits in the center of a galaxy, where clouds of gas and dust drift inward over long periods of time. As this matter approaches the black hole, it does not usually fall straight in. It has sideways motion, and because of that motion, it begins to orbit. The gas spreads into a thin, rotating disk around the black hole. This disk is called an accretion disk. The accretion disk is one of the most recognizable features in many pictures of black holes. It is the glowing ring, or flattened band of hot material circling around the dark center. But it is helpful to imagine it slowly. Far from the black hole, the gas may be cool and dim. It may glow faintly in red or orange, or it may not glow much at all. But closer in, as the gas moves faster and rubs against other gas, it heats up. It can become very hot, glowing in visible light, ultraviolet light, and X-rays. To human eyes, if we could safely observe it from far away, it might appear as a soft, bright ring, with colors depending on temperature, density, and the instruments used to view it. The disk could look white-hot near the inner edge, fading to yellow, orange, or red farther out. But many images of black holes use colors to represent invisible kinds of light, such as radio waves or X-rays. Those colors are often chosen by scientists and artists, so that we can understand the information more easily. The real appearance would depend on how close you were, what your eyes could detect, and how much material was present. Still, the basic idea is gentle and clear. A dark center, surrounded by a glowing disk, with the light of that disk bent by gravity. This bending makes the view unusual. If you looked at a black hole with an accretion disk from the side, you might expect to see a thin, flat line of light, like the edge of a record, or a wide glowing ring tilted toward you. But near a black hole, light from the back side of the disk can bend over the top and around the sides, reaching your eyes even though it began behind the black hole. Because of this, the disk may appear to curve upward and downward around the dark center. You might see the front part of the disk, and also the back part, lifted into view by gravity. The result can look like a ring that wraps around the black hole in a way that feels gently impossible. The disk is flat, but gravity makes it appear folded into the sky. The upper arc of light may actually come from the far side of the disk, bent over the black hole. The lower arc may come from another path of light, bent beneath it. Around the event horizon, the paths of light can be curved so strongly that the same part of the disk may appear more than once, in thinner and thinner rings. This creates a shape sometimes called the photon ring. It is a narrow ring of light near the edge of the shadow, formed by light that has traveled around the black hole one or more times before escaping outward. The photon ring would be very thin, very close to the darkness in the center. It is not the event horizon itself, but it helps outline the black hole's shadow. The shadow is larger than the event horizon, because light that passes near the event horizon may be trapped or bent away from the observer. So the black circle we might see is not exactly the size of the horizon. It is the dark region created by the black hole's capture of light. It is like seeing the silhouette of gravity. Softly, quietly, the black hole's shadow rests at the center of the image. It is round if the black hole is not spinning, or nearly round if it is spinning. Real black holes are expected to spin, because they form from rotating stars, or gain rotation as matter falls in. But even for a spinning black hole, the shadow remains close to circular in many cases. Around it, the light may not be evenly bright. One side of the accretion disk can appear brighter than the other. This is because the material in the disk is moving very fast. On the side where the gas is moving toward us, the light is boosted and becomes brighter. On the side where the gas is moving away from us, the light becomes dimmer. This effect is called Doppler beaming. So a black hole with a disk may appear as a dark central shadow, surrounded by a glowing, uneven ring, brighter on one side and softer on the other. This is part of why the famous image of the black hole in the galaxy Messier 87 looks like a dark center surrounded by a warm, uneven ring of light. That image was made by the Event Horizon Telescope, using radio waves gathered by observatories around Earth. The colors in the image are not exactly what human eyes would see, but they show the brightness of the radio emission. The ring appears orange and yellow, with a darker center, because those colors help us see the structure clearly. It is a real image, but it is also a carefully processed, scientific image, made from data. The black hole in Messier 87 is enormous, with a mass billions of times greater than the mass of the Sun. It sits at the center of a large galaxy, far beyond the Milky Way. Its shadow is not large in the sky, because it is so distant, but physically, it is very large. The bright ring around it comes from matter moving in the strong gravity near the black hole. There is another black hole that has also been imaged, the one at the center of our own galaxy, called Sagittarius A star. It is much closer to us than the black hole in Messier 87, but it is also much smaller in mass. Its image also shows a ring-like structure with a dark central region. Because the gas around it changes more quickly, the image is more difficult to make, but the general appearance is familiar: a dim central shadow and a surrounding glow. These images remind us that black holes are not simply holes in space. They are regions of curved spacetime. They change the paths of light. They shape the matter around them. They reveal themselves through their influence. And from far away, they can look very still. Even though matter near a black hole may be moving quickly, even though the physics is extreme, the image itself can feel quiet, especially when imagined at a great distance. A warm ring, a dark center, and the soft background of space. Let us stay with that image for a moment. A black circle, not painted onto the sky, but formed by the absence of escaping light. Around it, a ring of luminous gas, smooth and soft. The far side of the ring is bent into view. The near side lies across the front. The brighter side glows gently, because the gas is moving toward us. The dimmer side fades because the gas is moving away. Behind it all, stars are bent into arcs, their light curving around the invisible weight at the center. Everything is quiet from where we imagine ourselves watching. In space, there is no air to carry sound. Any sound we might associate with a black hole is a translation of data or a creative interpretation. The real view is silent. The motion is vast, but not noisy. The light travels across distance, and the black hole shapes it, slowly, steadily, without effort. Now, there are different sizes of black holes, and their appearance depends on their surroundings. A stellar mass black hole forms when a very massive star reaches the end of its life and its core collapses. These black holes may have masses several times that of the Sun, or more. On their own, they would be very hard to see. If they have no companion star and no matter falling into them, they may only reveal themselves by bending light or by influencing nearby stars. If a stellar mass black hole has a companion star, it may draw gas from that star. The gas forms an accretion disk, becomes hot, and shines brightly, often in X-rays. To our eyes, from a safe distance, we might see a small, intense disk of light around a dark center, though the actual event horizon would be far too small to see without extraordinary magnification. Then there are supermassive black holes, found in the centers of many galaxies. These black holes may contain millions or billions of solar masses. They can be surrounded by larger disks of gas, and in some cases, they power active galactic nuclei, which can shine across enormous distances. But even a supermassive black hole, if it is not actively feeding, can be relatively quiet. The one at the center of the Milky Way is active only at a low level compared with some others. It is there, massive and steady, with stars orbiting around it, and gas moving nearby. When scientists observe stars near Sagittarius A star, they see them moving in tight, fast orbits around something invisible. Those orbits reveal the mass of the black hole. The stars do not fall in, they orbit, just as planets orbit the Sun, though in a much stronger gravitational environment. So a black hole in space might look like a dark absence, outlined by motion. Sometimes it is outlined by glowing gas. Sometimes by distorted starlight. Sometimes by the paths of nearby stars. Sometimes by jets of particles moving away from its surroundings. These jets are found in some active black holes. They are narrow streams of particles and energy moving outward from near the black hole, along the axis of rotation. The jets do not come from inside the event horizon, because nothing escapes from inside it. They are launched from the region around the black hole, shaped by magnetic fields and rotating matter. In images, jets can appear as long beams or plumes extending away from the center of a galaxy. But in a quiet, sleep-oriented view, we can simply understand them as part of the black hole's environment, not the black hole itself. The black hole remains the dark central region. The surroundings tell us it is there. Now, if we imagine approaching the view more closely, still at a safe and purely imaginary distance, the distortions become more noticeable. Stars behind the black hole may appear to drift around it as you move. A star that should be hidden directly behind the black hole might appear as a ring of light around it, if the alignment is just right. This is called an Einstein ring. It happens when a massive object lies between an observer and a more distant source of light, bending that light into a circular shape. Around a black hole, this effect could be very strong. The background sky would seem curved and wrapped. A star field behind the black hole might be compressed into bright arcs near the shadow. Some stars could appear in more than one place at the same time, because their light takes different paths around the black hole before reaching you. This does not mean the stars are actually duplicated. It means their light has been guided along multiple routes through curved space. In ordinary life, we are used to light moving in simple lines. We see an object where light comes from. But near a black hole, the path of light can be curved into loops and arcs. The image becomes a map of space-time, not a simple picture. And yet, from far enough away, it can still be calm. The arcs are smooth, the ring is steady, the darkness is round, the stars remain small and quiet in the background. The idea of a black hole looking black may seem simple, but it is a subtle kind of blackness. It is not the black of a painted object. A painted black surface absorbs light, but it still has a surface. It may reflect a little. A black hole's darkness is different. It is dark because light from within a certain region cannot come out. The event horizon marks that region. Once light crosses inward, all future paths lead deeper in. There is no path back out to the wider universe. This is why the event horizon is sometimes described as a one-way boundary. To an outside observer, matter falling toward the event horizon would appear to slow down and fade, because of gravitational time dilation and redshift. The light from the falling matter would be stretched to longer wavelengths, becoming dimmer and redder. In practice, the details are complex, and matter would become part of the black hole's surroundings. But the idea is gentle to picture. Light near the horizon loses energy as it climbs away from the deep gravity, so the inner region appears dark. Around that darkness, the accretion disk may glow. But the disk does not have to be a perfect ring. It may be turbulent. It may have clumps, waves, and magnetic structures. It may vary over time. But in many simplified images, and in the way our minds gently picture it, it becomes a smooth, glowing band. A black hole, then, may look like a quiet eye of darkness in a field of light. But it is not an eye, and it is not watching. It is simply gravity, strong and concentrated, shaping the world around it. Let us think about color again, slowly. If you could see the hot accretion disk with human eyes, the inner parts might be bluish-white or white, if they are hot enough to glow strongly in visible light. Cooler outer parts might be red or orange. But much of the important light from black hole disks may be outside the visible range. X-rays are invisible to our eyes. Radio waves are invisible too. Telescopes detect them, and then scientists assign visible colors to represent them. So when you see an image of a black hole surrounded by orange light, that color may represent radio brightness, not literal orange gas. Still, orange and gold are often used because they feel clear, soft, and understandable. They make the ring visible. They show the contrast between brightness and shadow. In a real space view, the colors could be different. The disk could be intensely bright. It could be too bright to look at directly from close range. But from our calm, distant point of imagination, it is softened. The light is gentle. The ring is warm. The center is dark. The important shape remains the same: darkness surrounded by curved light. There is also the question of size. If a black hole had the mass of the Sun, its event horizon would be only about 6 kilometers across. That is very small compared with the Sun, which is about 1.4 million kilometers across. A black hole with 10 times the sun's mass would have an event horizon about 60 kilometers across. Still small in astronomical terms. A supermassive black hole, however, can have an event horizon larger than the orbit of planets. The black hole in Messier 87 has a shadow so large that light takes many hours to cross the region near it. The scale is difficult to imagine, but we can let it be simple. Some black holes are small and dense. Some are vast and central. All share the same basic feature, an event horizon, and gravity strong enough that light cannot escape from inside. But what would the shape of the black hole itself be? The event horizon of a non-spinning black hole is spherical. In images, its shadow appears circular. For a spinning black hole, the horizon is still rounded, though the space-time around it is dragged by the rotation. This effect is called frame dragging. It means that the rotation of the black hole twists the space around it, causing matter and light nearby to be carried along in subtle ways. Frame dragging can affect the accretion disk and the paths of light. It can help shape jets. It can shift the appearance of the shadow slightly. But again, the overall view remains close to a dark round center with light bent around it. A calm circle, a soft ring, a quiet bending of stars. If the black hole is viewed from directly above the disk, looking down along its rotation axis, the accretion disk may appear as a more symmetrical ring around the shadow. The brightness may still vary, but the shape could look more circular. If viewed from the side, the disk may appear more flattened, and the gravitational bending becomes more noticeable, lifting the far side into an arc above and below the black hole. This is why artist renderings show different appearances. The same black hole and disk can look different depending on viewing angle. The physics is the same, but the perspective changes. From above, a glowing circle. From the side, a warped band, curving around a dark center. From a distance, a small bright spot with a hidden shadow. From very far away, perhaps nothing visible at all. Many black holes may wander through galaxies unseen. They do not shine unless something nearby gives them light to shape. They are known through their effects. They pull on stars, they bend light, they heat gas, they merge with other black holes, producing gravitational waves that ripple through space-time. Gravitational waves are not visible light. They are gentle stretching and squeezing of space itself, traveling outward after massive objects accelerate, such as when two black holes orbit and merge. We do not see them with our eyes. We detect them with instruments that measure incredibly tiny changes in distance. So even when black holes do not look like anything, they can still be known. They are part of the universe's structure, quiet and hidden, revealed by careful observation. Now let us return to the image, because it is pleasant to hold it softly in the mind. You are floating far away, completely safe, in a quiet view of space. In front of you, at a great distance, there is a black hole with a thin disk of glowing matter. It simply turns, slowly from this faraway perspective. The near edge of the disk is a smooth line of light. The far edge rises gently above the central darkness, because the black hole bends the light around itself. The center is a deep, round shadow. Around the edge of that shadow is a thin, bright ring, delicate and almost still. One side of the ring is brighter, the other side softer. The whole shape rests against a field of faint stars. Some background stars appear slightly curved, especially close to the black hole. Their light is stretched into arcs, like fine threads around a dark bead. Farther away, the stars return to their ordinary positions. The black hole does not move towards you. It does not reach out. It simply exists, far away, as all massive objects do, with gravity that decreases with distance. From far enough away, a black hole can be orbited just like any other object of the same mass. If the sun were somehow replaced by a black hole of the same mass, and if we ignore the loss of sunlight, Earth's orbit would remain nearly the same. The gravity at Earth's distance would not suddenly become stronger, simply because the mass had become a black hole. This is an important and calming idea. Black holes are not vacuum cleaners in space. They do not pull in everything from unlimited distances. Their gravity depends on mass and distance, just like the gravity of stars and planets. They are unusual because so much mass is packed into such a small region, making gravity very strong close in. Far away, they are simply massive objects. Close in, space curves deeply. The boundary between these ideas helps us understand what we are seeing. The black hole looks strange because we are looking near the region where gravity is very strong. The light bends, the disk glows, the shadow appears. But at larger distances, the universe continues in ordinary ways. Stars orbit, gas drifts, galaxies turn slowly over millions and billions of years. In the center of many galaxies, a supermassive black hole rests like a quiet anchor. It does not hold the entire galaxy together by itself. The galaxy's stars, gas, dark matter, and overall mass all contribute to its structure. But the central black hole influences the region around it, especially the inner stars and gas. If enough gas falls inward, the black hole's surroundings may shine brightly. If little gas is present, the black hole may be dim. So what a black hole looks like depends on what is nearby. Alone, it is nearly invisible. With background stars, it is a lens. With a glowing disk, it is a dark shadow in a ring of light. With active surroundings, it may be part of a bright galactic center. With jets, it may be associated with long streams of emission reaching far into space. But the black hole itself remains defined by the event horizon, by the place from which light does not return. Now imagine the shadow more carefully. It is not a hole cut into a flat surface. Space is not a fabric in the literal sense, though fabric can be a useful metaphor. The shadow is an area in the image where light rays that would have reached you are instead captured by the black hole. It is a visual absence produced by the paths of light. The edge of the shadow is not perfectly sharp in every real observation. It may be softened by surrounding gas, by telescope resolution, and by the movement of material. But in an ideal view, the edge would be a clean boundary between escaping light and captured light. Just outside the shadow, light can orbit briefly. Some photons circle the black hole before escaping. This creates the narrow photon ring. It is a delicate feature, a very fine outline made by light traveling along highly curved paths. To picture it, imagine a ring within a ring. The broad accretion disk glows outward. Near the center, a thinner, sharper ring of light traces the boundary of the shadow. Inside that, darkness. The phrase photon sphere is often used for a non-spinning black hole, referring to the region where light can orbit. But those orbits are unstable. A tiny change sends the light inward or outward. Around spinning black holes, the situation is more complex, with light paths affected by rotation. Still, for a restful image, the concept is simple. Near the black hole, light can curve so strongly that it almost circles the darkness. This is why the black hole can appear outlined by light, even though it emits none of its own. The light belongs to the environment. The darkness belongs to the horizon. Now let your attention drift to the stars behind it. Each star sends light outward in all directions. Some of that light travels toward the black hole, passes nearby, bends, and then continues toward you. If the star is behind the black hole from your point of view, its light may curve around both sides. You might see two images of the same star, one on each side of the black hole. If alignment is nearly perfect, those images can stretch into a ring. The star is not moving in any special way. The light is simply following the curved geometry of space. Gravity, in this view, is not a force pulling light in the ordinary sense. In Einstein's general theory of relativity, gravity is the curvature of spacetime. Objects and light follow paths through that curved spacetime. A black hole curves spacetime so deeply that inside the event horizon, all future paths lead inward. This explanation can sound abstract, but the picture is gentle. Space around the black hole is shaped. Light follows the shape. We see the result as arcs, rings, and shadows. A black hole looks like curved light around quiet darkness. There is a peaceful symmetry in that idea. The object that cannot shine reveals itself by changing the shine of everything around it. Now we can compare a black hole to other dark objects in space, softly and slowly. A planet can look dark if it is not reflecting much light. But if a star shines on it, you may see a crescent, a day side, a night side, clouds, or a surface. A cloud of dust can look dark because it blocks background stars, but it has edges and texture, and it may glow in infrared light. A neutron star can be small and dim, but it has a surface and can emit radiation. A black hole has no visible surface. Its darkness is not shadow in the usual sense. It is the absence of paths out from within the horizon. This makes its appearance unique. And yet, to our eyes and minds, the most familiar image remains simple: a ring and a shadow. A ring because matter orbits and glows. A shadow because light is captured. Curved background stars because gravity bends light. Soft, uneven brightness because the disk is moving. These four features describe much of what we mean when we ask what a black hole looks like. Let the image repeat, gently. A dark center, a warm ring, a brighter side, a softer side, curved stars in the background, a silent region of space. The repetition is helpful, because black holes are not easy objects to imagine. They do not match everyday experience. But the visual pattern can be held calmly, without effort. In real scientific work, the images are made through long observation and careful analysis. The Event Horizon Telescope used many radio observatories across Earth, working together as if they were parts of a telescope as wide as the planet. This method is called Very Long Baseline Interferometry. It allows scientists to see very small details in the sky. The data from different telescopes are combined with precise timing. The result is not a simple snapshot like a phone camera image, but a reconstruction from measurements. Scientists test many possible images and compare them with the data. The final image shows the structure that best matches what was observed. This careful process turned the black hole shadow from a theory into something we could see indirectly through its surrounding light. The image is soft, somewhat blurred, and ring-like. That softness is not a flaw. It reflects the difficulty of seeing something so far away and so compact. It also gives the image a quiet quality, a ring of light, not perfectly sharp, surrounding a dark center. In that sense, the scientific image and the restful imagination meet each other. Both show something simple and profound, without needing noise or speed. Now, as we continue, let us imagine how the view might change if the black hole were surrounded by no disk, but the background stars were dense, such as near the center of a galaxy. In that case, the black hole might appear as a dark lens moving slowly across a crowded field of stars. As it passed in front of different stars, their positions would shift slightly. Some would brighten for a time, because gravitational lensing can focus light. This brightening is called microlensing, when the images are too close together to resolve separately. A black hole could be found this way, not by seeing the black hole directly, but by seeing how it magnifies a background star. To a distant observer, it might be almost invisible, except for a subtle change in starlight. A star grows slightly brighter, then returns to normal. Its apparent position shifts, then settles back. The black hole passes on, dark and quiet. This is another answer to what a black hole looks like. Sometimes, it looks like a temporary change in another star's light. Not an object, but an effect. Not a surface, but a signature. Space is full of such quiet signs. A planet reveals itself by dimming a star as it passes in front. A distant galaxy reveals mass through lensing arcs. A black hole reveals itself through the motion of stars, the glow of gas, or the bending of light. The universe often shows us things indirectly. and black holes are among the clearest examples of this. Now think again of the accretion disk, but in more detail, while keeping the tone gentle. The disk is made of gas, often hydrogen and helium, with traces of heavier elements. The gas particles orbit the black hole at different speeds depending on their distance. Inner parts move faster than outer parts. Because of this difference, layers of gas rub and interact. Magnetic fields thread through the disk. Friction and turbulence convert orbital energy into heat. The gas radiates that heat away as light. As gas loses energy, it gradually moves inward. It does not fall all at once. It spirals slowly orbit after orbit, closer to the black hole. Near the inner edge, the motion becomes very fast. Some material crosses the event horizon and is no longer visible. Other material may be driven outward in winds or jets. From the outside, we see the light released before the gas crosses the horizon. The black hole itself remains dark. The disk is the lamp. Gravity is the lens. The horizon is the silence. This is a calming way to remember it. The disk shines because it is outside. The black hole is dark because inside, light cannot return. The ring shape appears because matter orbits. The warped view appears because gravity bends light. Again and again, the same simple pattern. If the accretion disk is thick rather than thin, the view may be more complex. A thick disk can obscure parts of the shadow. Gas clouds can scatter light. Dust can absorb visible light and re-emit infrared light. Depending on the environment, the black hole might be hidden behind its own surrounding material. Some active galactic nuclei are bright, but difficult to see directly because dust blocks the central region. Observations at different wavelengths reveal different layers. Radio waves may pass through dust. X-rays may come from very hot gas near the center. Infrared light may show warm dust farther out. So the black hole's appearance changes with the kind of light used to observe it. In visible light, it may be hidden. In radio light, a ring may appear. In X-rays, hot inner regions may glow. Dust may softly shine. The object is the same, but each wavelength tells a different part of the story. This is true across astronomy. The sky does not have just one appearance. It has many, depending on how we look. Human eyes see a narrow band of light. Telescopes extend our senses. They show us radio, infrared, ultraviolet, X-ray, and gamma-ray views. Black holes are often understood by combining these views. But for falling asleep, we can let the complexities settle into one soft image. A black hole looks like a calm, dark center, held inside a ring of light, with space itself curving the view. Now, let us imagine the edge of the ring shimmering slightly, not in a restless way, but in the slow, natural variation of hot gas. Brighter patches move along the disk. Some fade, some appear. The flow is continuous. The disk is not solid. It is a river of plasma, circling in gravity. Plasma is gas so hot that electrons are separated from atoms. It responds to magnetic fields. Near black holes, magnetic fields can be important, helping move energy through the disk and sometimes launching jets. But the black hole does not need to be surrounded by anything to remain a black hole. The event horizon exists whether it is bright or dark. The glowing material simply helps us see the region around it. So if there is no material, the black hole may look like nothing, or like a gentle distortion. If there is material, it may look like a ring. If there are background stars, it may look like a lens. If it is in a galaxy center, it may be hidden within a bright core. Each answer is correct in its own setting, and in each setting, the central idea remains quiet, gravity shaping light. Now consider the term singularity, which is often mentioned with black holes. In general relativity, the singularity is a place where the mathematical description suggests density and curvature become infinite. For a simple black hole, it lies inside the event horizon. But the singularity is not something we can see. It is hidden behind the horizon. It does not contribute to the visible appearance directly. Modern physics may eventually describe the interior differently, perhaps with quantum gravity, which is not yet complete. But from outside, the event horizon is the important boundary. It defines the black hole's visible absence. So, when imagining what a black hole looks like, we do not need to picture the singularity. We picture the horizon's shadow, the bending of light, and the surrounding glow. The unknowable interior can remain quiet, beyond the image. This is fitting for sleep. Some things can be known by their edges, some things can be understood by their effects. We do not need to enter them. We can observe from far away and let the view be enough. Now let the scene widen. The black hole sits in a galaxy. Around it, stars orbit in vast patterns. Clouds of gas drift between stars. Some regions form U-stars. The black hole is one part of this slow cosmic environment. It is not separate from the universe. It is woven into it, through gravity, through motion, through light. At the center of a galaxy, a black hole may be surrounded by a dense cluster of stars. Farther out, spiral arms or elliptical star fields extend across thousands of light years. The black hole itself may be tiny compared with the galaxy, even if it contains millions of solar masses. Its direct influence is strongest near the center, but the galaxy is much larger than the black hole. From far outside the galaxy, you would not see the black hole directly. You might see a bright galactic nucleus, or perhaps a quiet central glow. Only with careful observation would the black hole be inferred. This helps put the image in context. A black hole is not usually a giant dark circle, visible against a galaxy with the naked eye. It is often small in apparent size, hidden by distance, and revealed through precise instruments. The beautiful ring images are close, magnified views of regions extremely difficult to resolve. But in our imagination, we can float close enough to see, while remaining safe and peaceful. The black hole is ahead, centered in the quiet. The ring glows softly. The shadow remains still. The stars curve gently around it. Nothing needs to happen quickly. Even the fastest motion can appear slow when seen from far away. There is another interesting point: calm and simple. If you were very near a black hole, looking outward, the universe behind you might appear distorted too. Light from many directions could be bent into your view. The sky might seem compressed, brightened, and curved. But we do not need to approach that closely. Our view remains distant. We are observers, not travelers inward. From our distant place, the black hole is an object in the sky, framed by space. It is useful to keep that distance, because black holes are easiest to understand when viewed from outside. Outside, there is the shadow. Outside, there is the disk. Outside, there is the lensing. Outside, there is time to observe. And slowly, the picture becomes familiar. A black hole looks like darkness that has shape because of light around it. It looks like a circle that is not a surface. It looks like a ring that is not solid. It looks like a distortion that shows where gravity is strongest. It looks quiet if we choose to see it from far away. Now, perhaps the accretion disk begins to fade in our imagination, becoming dimmer and thinner. The warm ring softens. The bright side becomes less bright. The dark center remains, but without much light nearby, it becomes harder to separate from the surrounding space. The background stars are still there. Their positions near the black hole remain gently warped. A few tiny arcs remain close to the center, but the black hole itself blends into the night. This is the natural state of many black holes, hidden until something illuminates them. There is something restful in that thought. The universe contains objects that do not announce themselves, but simply curve the paths around them. They exist quietly, known through patience. Astronomy is often the science of patient light. Light travels for years, thousands of years, millions of years, sometimes billions of years, before reaching our telescopes. A black hole's image is not only a view of space, but a view of time. The light from Messier 87 began its journey tens of millions of years ago. The light from Sagittarius A's star took about 27,000 years to reach us from the center of the Milky Way. When we look at such images, we are seeing old light, light that crossed space long before it arrived. The black hole shaped that light long ago, and only later did we receive it. This time delay adds to the quiet feeling. The image is not urgent. It is ancient light, arriving gently. Now, as the narration grows softer, let us gather the ideas one more time. A black hole by itself may look invisible. If it passes in front of stars, it may bend their light. If it is surrounded by gas, the gas may form a glowing accretion disk. The disk may appear warped, because gravity bends light from the far side into view. The center may appear as a dark shadow, larger than the event horizon itself. A thin photon ring may outline the darkness. One side of the ring may be brighter, because the gas is moving toward us. Colors and images may represent different waves